Hello, hi everyone. So, this is another lecture in the series of the lectures on removable partial dentures. So, the topic for today is biomechanical considerations in RPD design and support for distal extension basis. In class 1, class 2, and class 4 dentulous arches, the RPDs combine the support derived from abutment as well as soft tissues, resulting in greater stress during function. These forces hence need to be controlled to maximize the coverage over the soft tissues and to properly place the components so that stress or torque is not created on the abutment teeth. So now the proper design in removable partial dentures will contribute to the preservation of not only the remaining natural teeth or the abutment teeth but also aid in maintaining the tooth position and the stability of the process. So next, first let us consider what are the various biomechanical factors that affect the stability or retention and the functioning of a RPD. Now machines are classified as simple and complex based on their designs. There are six simple machines that are available today. This is not exclusive to dentistry and this is the basics in physics. So the machines may be classified based on their functionality. It may be a lever, a simple lever. It may be a wedge which acts as a fulcrum. It may be a screw, a disc, a pulley, or a inclined plane. Of these machines, the ones which are of particular interest in RPD will be explained in the next coming slides. In the removable partial dentures, in the mouth, they perform under the actions of two simple machines, that is the lever and the inclined plane principle. We have to avoid or reduce the effect of these two machines while designing of the cast partial denture framework. Now, a lever is a simple rigid bar supported somewhere along its length, and this is called as a fulcrum. So if you remember Archimedes, he had once said a famous quote that give me a lever long enough and I will even lift the earth. So this is what he meant by it. This long beam is acts as a lever, and anywhere where it takes support from a wedge or a sharp object is known as a fulcrum. So these two machines are of critical importance in our piece. So of the liver is again then further classified into three different classes based on the type of the liver. In the first order, the fulcrum lies in the center of the liver, and the load and the effort are at the two extremities of the liver. Whereas in the second order, the fulcrum lies at one end, the load is in the center of the lever, and the effort is at the other end. So the first example of class form is a simple hammer where we use it to remove a nail. When we remove a nail from a plank, the head of the hammer serves as a fulcrum, and the tongs or the prongs of the hammer that is used to remove the nail are the load bearing area. An example of the class 2 lever is a simple wheelbarrow that is used to take away coal or stones or any type of things, in which the effort is applied at the handles by the person and the fulcrum is at the wheels of the barrow. And the third order is the simple mechanism of lifting any heavy object using our arm, where the elbow serves as a fulcrum. Next, in the distillation RPD, the class 1 lever is the one lever which is of most importance. As the downward forces act on the denture basis, that is, in a class 1 Kennedy's class 2 bilateral distal extension situation, say when the patient is chewing a sticky food like a chewing gum or something, and the denture rotates around the occlusal rests on the terminal abutment teeth. So these terminal abutment teeth act as the fulcrum, and when any sticky food that tries to pull the denture away from the ridges or in a vertical direction is the effort, and the RPD moving in a vertical direction, that is along the sagittal plane, is the demonstration of the class 1 lever principle as shown in the figure over here. So we have to ensure that the abutment teeth, the retainer on the abutment teeth actively engages the abutment teeth during any lifting forces, thereby preventing its dislodgement and improving its stability. So now coming to the class 2 lever mechanism. As I mentioned, the classical example of class 2 lever mechanism is a wheelbarrow. So the wheel of the wheelbarrow serves as the fulcrum and the handles of the wheelbarrow serve as the effort. And this class 2 lever action is seen in the indirect retainers of a removable partial denture. So when the denture base is being lifted from the posterior region because of maybe any sticky food or chewing gums or any candy or such, then the denture rotates in a vertical direction, and the indirect retainers which are placed on the anterior teeth, that is far away from the fulcrum line, then they are the ones that display the class 2 liver action. Next, coming to what are the various forces that affect a cast partial dentures, there are basically three directions along which the forces are acting on the removed partial denture. One is along the horizontal fulcrum line, that is the classical fulcrum line which we take into consideration while designing a RPD. So this is the fulcrum line which passes through the most distal most abutments, and it is of critical importance in Kennedy's class 1 and class 2. So the dentures rotate along this horizontal fulcrum line in a sagittal plane, that is in a up and down action. The second is the sagittal fulcrum line. So this fulcrum line is parallel to the ridge and passes through the center of the ridge through the occlusal rest of the terminal abutment along the crest of the ridge. So this sagittal fulcrum line is basically important for the stability of the processes, because the processes will move in a buccolingual direction along this sagittal fulcrum line. So by extending the denture flanges and by extending the coverage of the major connector over the abutment teeth or over the hard palate, we can ensure that the movement along the sagittal fulcrum line is reduced or minimized. Next, and the last fulcrum line is a vertical fulcrum line. So imagine this is a vertical axis that is passing through the center of the patient's head, and the movement along this fulcrum line is appreciated in the horizontal plane. So this is the movement of the denture, that is rotatory or translatory movement of the denture along the vertical axis or the vertical line which passes through the center of the patient's head. So these are the three fulcrum lines that need to be considered while biomechanics in a cast partial. So the second is the quality of the support of the residual alveolar ridges, that is what type of ridges we have. The third is directly the clasp assembly, and which is further classified into the quality of the clasp assembly, the design, the length, and the material that is used for fabricating the clasp. And the fourth is the abutment tooth surface, the type of abutment tooth surface that is being used, that is whether it is a crown or it is a natural enamel on which the clasp assembly is being placed. And the last is the occlusal harmony of the RPD, that is the dentition should have a harmonious relationship with the antagonist teeth in the opposing arch. So now first let us see the length of the edentulous span. The longer the edentulous span, that is more the teeth are missing, the critical it becomes for the to make or ensure that the RPD remains stable in the patient mouth under function. So all these forces of the occlusion should be transmitted vertically along the long axis of the teeth. So, and this every effort must be made to place the direct retainer assembly directly on the terminal ends of the long edentulous span. And if we can save any terminal abutment, like even say a third molar or a second molar that may have a questionable prognosis, but if it can be saved, we should try to save them so as to reduce the length of the edentulous span. Next up is the quality of the residual ulnar ridges. Now, if we have tall rounded ridges, just like in complete dentures, we'll have good retention, we'll have good stability and support. Whereas if we have severely resorbed ridges or knife edge ridges or ridges with flabby tissues, then they will display poor stability, poor retention and poor support, because there will be nothing that will be resisting the movement of the RPD other than the abutment tooth. There are no tall rounded ridges or the firm mucosa over the ridges that prevents the movement along the sagittal fulcrum line or along the horizontal or the vertical fulcrum lines. So next is the clasp. So clasp, as I said, the quality of the clasp. The more flexible the clasp, the less stress will be transmitted to the abutment teeth, but also more stress then will then be transmitted to the edentulous or the tissue surfaces. Whereas the more rigid a clasp, the more stress will be transmitted to the terminal abutment teeth, and this can result in bone loss or torquing of the abutment teeth. So this is depending on the scenario, we have to decide whether we use a combination clasp or we use a cast clasp or we use a flexible wrought wire clasp. The second is a clasp design. We have to ensure that the clasp tip engages the infrabulge area, or only the clasp tip engages the undercut area on the abutment teeth, and the reciprocal arm should always be embracing the opposing tooth surface to prevent the undesirable forces on the abutment teeth. And the third is the occlusal harmony. Now, Just like complete dentures, which ensure that we are able to produce a balanced occlusion. The teeth should be arranged over the crest of the residual ridge in the mandible and buccal to the ridge in the maxilla. We should use denture teeth which are slightly less buccolingual width than the actual natural dentition, and we should concentrate the contact with the opposing dentition on the center of the ridge, and especially the contact should be with the opposing dentition on the second premolar and the first molar. These two teeth are the most important that should have a good occlusal contact with the opposing dentition. So occlusion, as I mentioned, occlusion with the first, second premolar and the first molar in a distal extension is very important. This should not be what you call taken lightly. And second is the denture base extension. The denture base should extend as much of the uh, residual alveolar ridges, that is up to the mucobuccal fold or the mucolingual fold, thereby increasing the surface area of the denture base and thereby reducing or minimizing the stress that is generated during the chewing or mastication. So it's just like the snowshoe principle that we see. And next is the type of the major connector we select is also very important, especially in the mandibular. The lingual plate is the major connector of choice, and in the maxillary, the anterior-posterior parietal strap or the complete parietal coverage are the best major connectors that offer the best rigidity. The minor connector also should be snugly fit on the inclined surfaces of the teeth, and there should be no space between the minor connector and the embrasure area. This will result in foot and plaque accumulation and secondary caries. And also, as we know, minor connectors, when they are snugly attached to the abutment teeth or the vertical or axial walls of the abutment teeth, they offer good amount of indirect retention as well. The next is the rests. Now, rests are also very important in RPT design considerations, as the rest act as the fulcrum during the any functional movements or chewing or masticating. So the entire RPT pivots around the rest, whether they are the primary occlusal rest or secondary occlusal rest, as we see in indirect retainers. So they should be designed in such a way that the floor of the rest is sloping towards the center of the tooth, and thereby it prevents the slipping of the RPD during function and also directs the occlusal forces along the root length of the abutment teeth. So these are all the factors and design considerations, that is biomechanical design considerations, that we must know prior to designing of the RPD framework. And once we know these, then we can better understand the principles of RPD designing, and we can therefore design a framework that ensures all the three components, that is the retention, stability, and support of a cast partial denture framework. And that brings us to the end of this lecture. Thank you all.